Porous Media Tea Time Talks. We are part of Interpore Young Academy and we aim to spread the Porous Media science among young scientists. I am Nara Brandão from the Federal University of Uberlândia in Brazil. And today in the studio with me, we have Mohammad from University of Oslo, Javier from Los Alamos National Laboratory, and Kamal from Radboud University. Please feel free to subscribe to our channel and stay tuned to our talks. Today we are going to have two great presentations from Kondi and Stephan. At the end of each presentation, we are going to have 5 minutes for question and answer. So we appreciate your participation in the chat box on the right hand side. And our first speaker is Kondi. He will talk about an exploration of hysteresis and dynamic effect in porous media. Kondi has a bachelor's and a master's degree in mechanical engineering in India. He did his PhD in Eindhoven in the Netherlands and Hasselt University in Belgium in 2019. Currently, he is in his third postdoc at Radboud University in the Netherlands. His focus is on applied and numerical analysis of nonlinear degenerative PDEs, especially resulting from porous media flow problems. So, Kondi, you are welcome and the floor is yours.
Okay, thank you, Mara, for introducing me. So, hello, I'm Kondi. I'm a big fan of the Interpore community, and I have attended all the Interpore conferences till 2016. And hence, when I was asked to give this presentation, it was a very big honor for me. So today I'm going to talk about hysteresis and dynamic effects in porous media flow, which is a topic very close to my heart. I have been working on it for last 7 years, and it roughly constitutes half of the total body of scientific work I have done. But it is also interesting because it illustrates the scientific method at work. So what do I mean by this? There were some experiments, and from the experiments we proposed some models, and then we analyzed them using mathematical techniques, and then we made some predictions, and these predictions were later verified using simulations. And finally, we could explain a plethora of physical phenomena. So coming to the current topic right away, let's understand what I mean by hysteresis. So I have a small illustration. So let's say we have a porous media like soil, and then we pour some liquid onto it. So the liquid goes in very easily in, but it takes some time for it to settle down to an equilibrium state. Also, if we now try to suck this liquid out of this porous media, we need a much higher pressure and effort. So hysteresis actually refers to the discrepancy of the affinity of water to go in compared to the difficulty faced when you try to drain it out. And this was known for about 100 years. So for example, in this paper in 1931 by Richards, where he discusses his namesake equation, he already shows the evidence of hysteresis. And this has also importance in naturally commonly occurring phenomena like horizontal redistribution. So if you put a wet block in touch with a dry block, then you would expect that the water will flow from one block to the other block. And hence this effect of hysteresis will be very important in these cases. Now also, as I mentioned, that it takes the water to settle down in some time. So there will also be a dynamic effects involved. And these dynamic effects play an important role in stuff like saturation overshoots. So in this experiment by Di Carlo, it was shown that in a long sand column, if you inject water hard enough, then you get this local maximum of saturation, which are known as overshoots. And this cannot be explained by equilibrium or standard models, right? Then there are phenomena such as gravity fingering, which require both hysteresis and dynamic capillarity to explain. So in this talk, we will be proposing models for the above two effects, and using this model, we will do the mathematical analysis to kind of give justifications of why this bottom three phenomena occur. Okay, so first thing first, let us move to the hysteresis models. Now there's literally tens, if not hundreds of different hysteresis models. And in no point in this talk, I'm going to claim that the models we are going to use are the best one in all scenarios. But the models we are going to use are going to be simple enough so that we can use mathematical tools to predict the phenomena that we want to discuss. And a good starting point for this will be the plate type hysteresis model, for example. So say we have the Richards equation, which equates the water saturation with water pressure. Then the plate type hysteresis model proposed in this paper relates this pressure and saturation by this menacing looking term. So if you ignore the second thing, then you end up with this equilibrium or a standard model. But the second term incorporates the effects of hysteresis. So what do I mean by this? So in this picture, you see the effects of hysteresis. So if you measure this pressure of water in terms of saturation, while water is always going in, then you get this blue curve. Whereas if you measure it when water is always coming out, then you get this red curve. But then if we switch from water going in to water coming out in an in-between point, then you get something like the yellow curve, which is known as scanning curves. And these are how it looks experimentally. Now the plate type hysteresis model approximates this curve by a vertical straight line. Now, of course, there's troubles associated with this approximation. And for example, in a lot of situations like the horizontal redistribution I mentioned earlier, you don't get out of the plate type hysteresis model meaningful physical solution. For example, your pressure can become indeterminate. So there was a need to extend this model, which we did by proposing the extended plate type model, where we use this expression to relate pressure and S. So instead of a time derivative of saturation, it has the time derivative of saturation plus a function B of the pressure. And then we showed that by tuning this function B, we could actually make the scanning curves look much more like the experimentally obtained scanning curves. And we can also further make it thermodynamically consistent in the sense that it will be increasing in terms of entropy. Now we can use this extended model to cover all cases of horizontal distribution, including the unconventional flow cases, which could not be modeled by plate type hysteresis. Now this result was published in this paper below, but we went one step further and proved that there will always exist a weak solution for this model, even in degenerate cases, which puts this model under firm, rigorously mathematical grounds, right? So this result is published in this paper. Now, if you want to further incorporate the effect of dynamic capillarity, then we need to extend the hysteresis model by adding this tau dTs term, which was first proposed in this paper by Majid and Gray. We can do the same. So this is for the plate type hysteresis model, but we can do the same for the extended plate type model by also adding this tau dTs term. And now we are in a position to actually go forward and analyze overshoots, and we will do this by traveling wave approximations. So if you have a long cylinder of soil and if you inject water from one side, then you can approximate the profiles when it is developed by traveling waves moving at a constant speed. And then you can analyze these traveling waves, and using this technique we can say that, okay, for only capillary hysteresis, if there is no dynamic effect present, apologies, then you will have the traveling waves, but it will never cause overshoots. Whereas if you have the only dynamic capillarity effect, then you will have overshoots if this parameter tau, dynamic capillarity parameter, is given that is greater than a given a known computable constant. And we can also further develop criteria of when this overshoot will reach maximum saturation of 1. But if you look at the picture on the right hand side, then you will see that it actually doesn't look too much like the experimentally observed scanning saturation profiles. And so in a follow-up paper, we combine the plate type hysteresis model with the dynamic capillarity, and then we get profiles which look more similar to the experimentally obtained curves. But in 2016, when I presented this result in Interpol Rotterdam, then there was a question from the audience that, okay, the main overshoot looks similar, but our theory predicts that there will be infinitely many secondary overshoots, which is not observed from the experiments. So I thought about it a bit more, and then if I put extended plate type model to model hysteresis and then add dynamic capillarity to it, then we can show that there will be only one major overshoot and maybe finitely many secondary overshoots, but they will be minor. We can also extend this result to the two-phase flow case, where the main flow equation is the Buckley-Leverett equation. In this case, we can also show the existence of all traveling waves. And further, we can go one step beyond and prove the existence of entropy solutions in the hyperbolic limit, which is the solutions which come out when the domain is very large, like in a reservoir scale problem. Now, the entropy solutions for the equilibrium models have been known for about 70 years now, first derived by Oleinik. But our solutions, if we incorporate also the hysteresis and dynamic capillarity, then these entropy solutions will look radically different from the standard Oleinik entropy conditions. For example, they can have this a stable saturation overshoot, which is not there for the standard models. And some experimental observations are also there which support the existence of this kind of entropy solutions. This result was put in this publication, but there was one particular case that intrigued us even more. Now imagine again that there is a bottle of half filled with water below and half filled with oil, and now you turn this bottle overhead. Now what you can expect is from the standard theory that the water saturation will look something like this profile, this red profile. But if you incorporate hysteresis, then we can prove rigorously that actually there will be a jump at this point of contact in the entropy solutions. And there can be two modes of this jump. If this difference is small enough, then this jump is still looking kind of similar to the old entropy solutions. But if this is large, then this jump can make the solutions look completely different from the standard model. And this can have deep consequences in, for example, oil and gas extraction. And it flies in the face of the established theory of entropy solutions. So we thought that it is a very important result also to highlight. Finally, I briefly mentioned the gravity fingering phenomena also. So say we have a homogeneous block of soil, and then on top you have a high saturation regions, and in the bottom you have on top you have a high saturation region, and in the bottom you have a low saturation region. Now, due to gravity, you would expect this water front to move below. But if you start with a planar front, then you might expect that your front will remain plane at all times. But this is not the case if you observe from experiments. In fact, it will immediately develop into these fingers, as you see in these pictures in the right hand side. And these fingers are actually the preferred pathways of water to travel. And these fingers are very curious because they have a higher saturation, whereas in the just area beside them, there is this black region which is almost completely dry, but still this water doesn't seep into this dry region, which means that fingers are stable. Now, it was known that you need both hysteresis and dynamic capillarity to kind of explain this situation. And from numerical experiments, it was known that all these fingers in a homogeneous soil should move with a constant speed. Now, if you put a frame in these fingers moving with that same speed constantly, then in this frame, the finger looks kind of static, right? And this motivated us to consider a traveling wave problem moving along with the fingers. And if you find the solutions of this problem for a given given wave speed, then we can also explain how the fingers are formed. So long story short, we could prove that non-1D traveling wave solution, finger solutions do exist with a given wave speed. And we could also show that this solution has a structure where there will be a free boundary, beyond which there will be a hysteretic dominated region. And because of this hysteresis, because it's difficult to dry out the finger, dry out for water from the region which has high saturation, these fingers will become stable. We can also come up with an algorithm which can give these results as we have shown below, numerically results. And this result is also now submitted. Finally, I come to the end of the talk. So I would like to thank all my sponsors, without whom this research would not have been possible. And a great vote of thanks to you for tuning in and listening on. Thank you.
Thank you, Kundi, for this wonderful talk. It was really insightful and interesting. I'm going to ask first question of my own. Can you elaborate more about the extended play type model? What is the modifications to drive this model in terms of theory and also in terms of
mathematics? Let me very quickly go back there. So the extended play type, as I said, like the play type model, what it does, it approximates this scanning curves by a vertical line, whereas this extended play type model approximates it with inclined lines. And you can, by tuning this function B, you can actually choose which inclined lines you want. And that, in many situations, is a more physical thing, because if you have this vertical lines, then sometimes you come up with really physically not so meaningful solutions.
Okay, so basically it comes from mathematics, not from any direct observation of the.
No, so there is this paper that I mentioned also earlier. Well, it comes from observation because the scanning curves in experiments are inclined also, but it also, there is a justification of it from this very same paper by Bilayev and Hassanizadeh, where they proposed the play-type hysteresis model. They actually showed the criteria of what a model has to be to be thermodynamically consistent in energy increasing. And they showed the general form which will be energy increasing will be this form given by the extended play type model. So this is actually a physical, there is a physical argument behind why this model can be considered.
Wonderful. The second question is by Stephan Berg. What if you use the geometric state variables, Minkowski functionals, to parameterize capillarity, i.e. there would be no hysteresis?
Yes. So thank you, Stephan. I know Stephan for a long time. And thank you for your question. I know you are very much interested in that topic. And as I claimed in the very first sentence on the hysteresis model, because I know there is a lot of conflict between communities in this one, that this model is not representing the most, I cannot claim that this is the most physically correct model in any way. But still, it is the simplest model, because in this Minkowski kind of models, you need to incorporate interfacial area, you need to incorporate Euler characteristics, which makes the model much more complicated. And so it is very difficult to analyze this mathematically and tell and say confidently what is going on. So our motivation in this analysis was to stick with simpler models which we can analyze and give justification of why some physical phenomena is occurring. But you're right, if we go to, and by the way, this interfacial area and Euler characteristics, to determine them, you have to really look at pore scale imaging and stuff like that to determine these conditions, which sometimes we do not have. So in that sense, okay, I think this is actually not so bad model if you just want to describe the physical phenomena.
Perfect. The next one is by Hosseini Nassar. Where was the specific application in this study?
Where was the specific application? So first of all, for example, in the fingering case, I would say that the fingering, because if you have oil and gas extraction and there's this finger formations, then main flow of the fluid or the oil is through this finger. So it is really important, and there has been a lot of studies which mostly look at the heterogeneity which triggers these fingers. And this has importance in the oil recovery sector. But here we also claim that not only heterogeneity, but hysteresis and dynamic capillarity itself are one of the triggering mechanisms behind the causation of fingers. And also in the case, for example, this entropy conditions I showed you, these entropy conditions in the paper were actually markedly different from the standard entropy conditions, and they are many times used in traditional hyperbolic solvers, this Oleinik standard entropy conditions, to predict stuff in the reservoir scale. But my claim is that if we incorporate hysteresis, then you can actually have completely different set of entropy conditions, which might have very deep consequences in the field of reservoir simulation.
Before asking the last question, I have two comments from Stephan. The first one is, but the hysteresis model is completely phenomenological, and the other one is that, and not really physical.
Yes, but you see, like I guess also in the second talk where Stephan will talk about it, to derive a hysteresis model from the very first principles. So you see, you come across many difficulties in doing that. And it's a very challenging thing. So of course, at some stage, you are using approximations, whether you stick to a more physical model or you look at an upscaled model like this, right? So it depends on what your aim goal is. Of course, there are applications where you have to be very accurate physically, and then you might need to shift to more accurate models, and maybe you have the information from the pore scale. But this can be used as a upscale model, which is more or less physically consistent, that can be used to predict these things and to understand things better, rather than to use it for very accurate predictions.
Wonderful. And the last question from your previous supervisor, Sarim Pop. Nice talk, Kundi. You mentioned a finite number of oscillations in the tail. Can you elaborate on this? Do you have a criterion when you get a certain number of oscillations? Aren't these infinitely?
Yes, so there is a criteria which is associated with the, yeah, we can give a criteria of how many oscillations there will be, but this criteria can be a bit imprecise. But at the end, what it comes down to, why there are finitely many oscillations, is because these slopes are inclined. So the scanning curves are inclined. And if you have, you can imagine, if you have this vertical jumps happening, then in a very short interval, you can have infinitely many vertical jumps. Whereas if you have this inclined profiles, then if you cannot stack up many in a single interval. You cannot put too many inclined scanning curves, and that is the justification from physical point of view why there are finitely many. But to be really honest, this comes out of the mathematics, and I don't have a very concrete idea of what it means physically.
Very nice. Okay, thank you for your for this great talk and for the Q&A. I guess now it's time to move on
Shall I
to our
stop
second
sharing?
speaker. Yeah, our second speaker today is Stephan Benjamin Lunowa. He obtained his Bachelor of Science in Simulation Technology at the University of Stuttgart in 2016. He graduated with honors in the Joint Master of Science program, Simulation Technology and Industrial and Applied Mathematics from the University of Stuttgart and Eindhoven University of Technology in 2018. Subsequently, he became a doctoral candidate in the Computational Mathematics group at Hasselt University of Belgium under the supervision of Professor Sarim Pap. His research interests comprise the mathematical modeling and upscaling of two-phase flow at the Pore scale, as well as numerical analysis and simulation of two-phase flow at the Darcy scale, involving dynamic capillarity and hysteresis. Thank you, Stephan, for accepting our invitation, and the floor is yours.
Yeah, thank you very much for this kind introduction. And yeah, I'm also very honored to be invited in these media tea time talks. So as already announced, I'm kind of continuing what Kundi was talking about. But instead of the Darcy scale, I'm more focusing on the Pore scale. So I was looking into what happens in the Pore scale concerning exactly those interfaces also Stephan Berg was talking about. What are the dynamics involved between the two phases that make these dynamic and hysteretic effects happen? And first of all, I want to thank all the people I work with, Arjen Maschini, Tom Bultrace, and Berle Knudde from Ghent University, as well as Carina Bringedal from University of Stuttgart and Soren Pop here at Hasselt University. So as a short motivation, we already saw it before. Basically, if you look at the scanning curves between imbibition and drainage, you see that these hysteretic effects and dynamic effects play a role depending on where you start with the saturation. And whether you do the imbibition or drainage scan, you get different curves, and you might even get these overshoots as seen on the right. So I will first talk about this mathematical model in single pores. Then the asymptotic expansion and upscaling I use to derive averaged models. I'll show a short example in 2D. And in the end, I will also talk about validation we did in the case of capillary rise experiments. So for the mathematical model itself, what we're basically looking at is a simple model where you have one long thin pore, either in 2D as a thin strip or in 3D then as a thin tube. And basically on one side you have one fluid and on the other side the other fluid. And both fluids are described by the classical Navier-Stokes equations. And then at the boundaries, left and right, you have in and outflow conditions. And the center line, you just have symmetry conditions. And the important part now is to make the interface able to move. You need some kind of slip condition at the outer wall. And there you can either describe a local Navier slip condition close to the interface point, so the moving contact point where the interface and the wall touch, or you can do this globally. There are also other conditions possible to make the interface move, but this is kind of the most simple way to describe that slippage which occurs to make this moving contact line happen. And then finally, between the two fluids, you have this interface which is driven by the flow and the surface tension between the two fluids. And there we additionally allow the contact angle, which must be prescribed, to be dynamic or even hysteretic itself. And this can also be seen in experiments. If you have such tubes and you push in water, on the one side, the contact angle with increasing velocity will change. And if you then retract the fluid again, the contact angle will have a different value. So you really have dynamic effects depending on the speed of the interface moving, but also hysteretic effects depending on the direction. Then from this model, what we basically do is a scale separation. So we assume that the radius in comparison to the length is very small, defining in mathematical terms a small epsilon. And then we use an asymptotic expansion ansatz. So we expand all the quantities in orders of epsilon, meaning that the leading order terms are the important terms we look for, and all higher order terms are then secondary effects which can be included but are not necessarily the most important things. Then we equate the terms of the same order, in our case the highest order, and that means that in the limit as epsilon goes to 0, those equations then hold. Then for the main assumptions, just for completeness, the most important things are that the capillary number is very small, so you have a capillary effect actually at the interface, that there is a transversal interface, it's directly along the transversal, not somehow going through the whole pore. And as I said, either a global constant slip or you have some slip close to the interface, vanishing exponentially. Then if you derive all those equations in the bulk domains, meaning away from the interface, in each of the fluids you just get a classical Hagen-Poiseuille flow. And then if you average this transversally, what you also get is then a classical Darcy's law, as it's known for single phase flow through pores, where the average velocity is proportional to the gradient in pressure and the gravitational effect. And this permeability then depends quadratically on the radius. So for 3D, that's just a classical 1/8 radius squared relation you get for tubes in single phase flow, now also depending on the slip parameter lambda. And for the thin strip in 2D, that's basically this 1/12 diameter squared relation you get for the Couette flow. Then, of course, it's important to couple these two regions at the interface. And there, in a small region around the interface, what you basically can derive is that you have a constant curvature, and the interface movement is given by this differential algebraic equation, which looks quite complicated, but what it basically boils down to, when you average it, is you get a dynamic capillary pressure relation, which involves 3 terms. So basically, what you do is you average over the first phase, you average over the second phase, and in between you have several terms. What you will get is this local capillary pressure term coming from the interfacial tension, which is directly related to the dynamic and hysteretic contact angle. Then you have a gravitational term coming in from the different density of the 2 fluids. And finally, you get exactly this type of dynamic effect you have on larger scale, tau of S, dTs, depending then on the viscosities, the permeability, and so on. So from a pore scale, simple 1D model, we can actually see why these terms appear even in a single pore. And if we look now into an example, what I considered here is basically a constricted pore. So you have fluid coming from the left. In the center, it's a bit thinner. So there everything speeds up, but also the capillary pressure will be higher there because the radius is smaller. And then what we do is basically just pushing in water, then reducing the pressure slowly that it moves back to the entry point again. So what you then can see over the course of time, or also saturation if you compute it via saturation, is that you start pushing things in, you get one curve, then at some point, if you use the hysteretic curve or also the dynamic curve in blue or red respectively, you have this change to the other slope where you basically get the same profile turning around but at a higher position. Meaning that actually you get somehow these more or less these Leverage J functions, sorry for that, but shifted exactly by this hysteretic part or by the dynamic part if you only go for the dynamic effect. So in that sense, we can actually justify why these plate-type hysteresis models do make sense to consider on the larger scale. Now, of course, up to now, I have only shown equations. So the question arises, how can we validate that such things are relevant? And for that, I want to present a simple application of capillary rise. So there you have a rise of a liquid in a vertical glass tube. For the model, we use this kind of linear contact angle model as it comes from molecular kinetics theory. Then the effective model looks like this. That's interestingly more or less the Lucas-Washburn equation, just incorporating this slip effect and the dynamic contact angle effect. And what it means in comparison to Lucas-Washburn, you can see in the lowest equation showing the solution. Basically, what you get is on the right-hand term, which is just the classical Lucas-Washburn equation, where the time depends quadratically on the half of the rise. But additionally, you have a linear term where it gets slower due to the dynamic contact angle, which retards the movement because it decreases actually the capillary effect. So with this dynamic parameter, you actually have a slower increase in half over time. And on the opposite, if you have slip, then the in total, it will move faster towards the non-dimensional total height 1. So we compared this to experiments done by Schmati and Piri. And for glycerol, we saw that, yeah, of course, you have this one parameter you have to fit. But with this exact one parameter, which is more or less the same for all radii, you get a very good agreement. And I have to say here, I'm only showing the capillary rise of glycerol, but we have similar results for saltrol and also for water, although there you have to also incorporate the effect of inertia. So now that I've shown the model on the pore scale, the validation of it, just some conclusion and outlook. So basically what we looked into was a thin strip and thin tube model for two-phase flow with moving contact line. And then if you derive the leading order solution, what you get is Darcy's law and a dynamic and potentially hysteretic capillary pressure relation, which you can we validated against capillary rise experiments. And now, of course, the question is, yeah, but that's only one pore. So what does it have to do with a big reservoir where you have millions, billions of pores? And so the next step for us, what we would like to do is to upscale this by using a pore network model where within the network, each pore throat recovers exactly this upscaled model for one pore I showed previously, and then looking at the whole effect of the complete network. And for this, we have already preliminary results where we just stack several pore throats, and then you basically get again the capillary rise experiment using also several pore throats stacked on top of each other, directly connected. Then, of course, the next step is to also incorporate bisections and things like that. Then, of course, having that scale, there's a need for further model validation. And there are many other topics I didn't discuss, for example, wall roughness, where you then get into the issues of pinned contact angles, heterogeneity, when your contact angle locally depends on the chemical composition of your structure, or more general geometries. So with that, I want to thank you for your attention, the FWO and the Hasselt for the funding. And if you're interested more into the topic, the first part I discussed is given in this first reference, and the second part in the second. Thank you very much.
Thank you very much, Stephan. This was a very interesting talk to see the mathematical modeling in detail of pore scale phenomena. And I guess I have a question of my own. It's very interesting to see how this is done on a single pore, maybe with a slight constriction. But can you talk a little bit about how can also other important pore scale effects can be included, such as Haynes jumps or capillary trapping, or all these things that tend to affect macroscopic flows as well?
Yeah, I mean, Haynes jumps, it really depends on the time scale you're looking at. Because in practice, I mean, of course, in measurements, typically they are too fast to be captured. But in principle, that's also just a continuous movement of the interface. So I would expect to actually have it already covered within the model itself, just on a shorter time scale. And then the question would rather be to how to not need to resolve this fast time scale, and instead just look at it like an Haynes jump. Yeah. Then for other effects, of course, you have to really look into the detailed distribution. So that's why I said one of the main assumptions in my model is this transversal interface. Because if you have effects like snap-off or a layered flow, then you get a completely different models in the end, and you have to account for these then on the different regions where they occur.
Excellent. Thank you. We have some questions from the audience. Is mainly Stephan Berg, and I'm gonna try to summarize them a little bit. But at first, he asks, is that if the contact line, for example, the water-oil interface, is moving with the solid?
It's moving itself. So I mean, you have the triple point in 2D or the moving contact line in 3D, and that one is allowed to move freely within the pore. So that's why we need the slip condition to make it possible for the contact line to move, and the solid itself is fixed.
All right. Thank you for your answer. And now Stephan says he's asking if the pore scale displacements, like the question that I asked you, or for example snap off, is it associated with different relaxation times in this model? How is it accounted?
Yeah, I mean, basically, what we see from the model is this kind of Haynes jump occurring is actually due to the different radius, which means on the one hand, a smaller radius actually increases the capillary force due to because it's related 1/r. And at the same time, it changes the dynamic effect because at this constriction, you will have a higher flow speed. So it affects both terms, and therefore, yeah, of course, it really depends on this constriction, how it will change the effect on the model.
Excellent.
It definitely can be seen already from this model that it depends on these characteristics, yeah.
Thank you very much. I don't know if the rest of the Porous Media Tea Time Talk family has any more questions. Well, otherwise, we'd like to thank again Stephan for this fantastic presentation.
Thank you very much for the invitation.
All right. So thank you very much to all the rest of the YouTube audience for joining us, and we would like to invite you to the next session, which is in March 29th. It's going to be very interesting. We have two very interesting presentations. The first one is about X-ray tomography imaging of crystallization by Victor Okumko. And the second one is about a trending topic, which is modeling fugitive methane emissions, which will be quite enlightening, I think, by Kenza Busnari. So we would like to invite you, and we hope to see you there. Thank you very much.